Hi everyone. Today we're recording after the actual session took place, so somehow things are not exactly real time as they happened in the class. The idea of this workshop specifically, of this session specifically, was to have a hackathon, somehow take everything that was earlier discussed in the practical sessions and try to get people to have their hands dirty. So somehow we're narrating after the fact what happened, trying to recreate the whole content. So what happened was that we had 5 teams participating. One of them had 1 person, and the other were between 5 and 3 people. And more or less, we had an IPython notebook. We walked them a bit through the ideas of what we want to do. We gave them some hints on what might be the best strategy to improve upon a baseline. And then we let them get their hands dirty, actually experimenting on a small scale from the point of view of training epochs. So somehow they had, everything was in Colab, so they had no GPU computation, most of them. One team managed to enable some GPU credits they had. And they tested on the small scale, and then we did a blind test. We asked them to submit code to us. We took the code and ran it for a long time, and then measured on the test set rather than the train set, in order to see whether some people could outperform a relatively strong baseline we came up with. Somehow, the small model that we talked about earlier, but a bit enhanced. So the first step of this talk is about walking you through the IPython notebook. Which we can find here. And we can directly open it in Colab. So more or less from the GitHub, we just open into Colab. All that's required is that we have a Google account. Now, when you are working in Colab, you get some reduced computational capacity for free. But a bit of an issue is how do you stage your data there, right? So the first thing we got to do is that we got to take the data set and put it in our Google Drive, right? That's you take the URL and you just add it to your Google Drive somehow. There's different ways of doing it. And once you have the data in your Google Drive with the correct file name, what we have here in the first step is a bit of a complicated piece of code, a bit cryptic. What we're actually doing in this step is that we are mounting our Google Drive onto the inside the Colab virtual machine as a partition. We're mounting it in a folder, and then we copy whatever we want from our drive, in this case just one huge file, about ½ GB, and we unmount very quickly, because as long as our Google Drive is mounted in the Colab, we could even erase stuff by accident. So somehow this is the only part of the code where if you play with it, you might end up harming your Google Drive data. So if you want to edit it, be extra careful. So in this case, we might be asked to authorize our Google Drive. We might have to say yes and select our Google account and whatever, because we are granting one Google service the opportunity to read data from another, and the policy is that that shouldn't be doable without consent. And the other thing we need to do is that a Colab machine is essentially a Linux virtual machine. We only get to experience it through a Python notebook, but under the hood, it is a Linux machine, right? So whenever we put an exclamation mark, as we do here, whatever we write are commands that are done in the shell. And that's the way, for example, with which we can install Python packages we're missing. So in this case, what we're doing is that we are installing Tensorboard X. That's an extra thing that standard Colab instances don't have. And we need to install it. So in this case, what has happened is that I rehearsed this a bit earlier, and the virtual machine that Colab assigned to me is still open and it's still the same. So these things might happen a bit faster than they would on your machine. That's why you see whenever the messages are that things are already there. Do expect a bit more output when we do things, and do expect a bit more time when installing or unzipping data or whatever. But actually the same commands work out of the blue for anyone. Okay, so more or less what we've done in these two first steps is that we have staged the data inside Colab and unmounted our Google Drive, so we don't have to think about that anymore. We have installed or made sure that Tensorboard X, which we're going to talk about later, is already installed. And now we're beginning our normal, let's say, Python notebook, right? Somehow, if we were sitting on a PC, probably this would be the point where our notebook begins. So we install all the dependencies. We import all the modules we depend on. And then this whole notebook is meant to be making use of your GPU if it is there, but not require it. So somehow, in order to do this, we have to set the device, and we have more or less a small debug message on whether it managed to see whether we have a GPU or not. If you have a GPU and you get that message, it means you have something wrong that needs work with. So, as we said in the earlier versions of this PyTorch introductory tutorials, a good point to start with is defining the preprocessing of images. So in this case, we choose to have two different ones, right? One for training and one for inference. The reason being that in the training we are doing a bit of augmentation, a bit of data augmentation, just to show a bit what that would mean. As we can see, what these pipelines do, right? These are small pipelines of preprocessing we have defined. We have two of them. Is that the first one is that no matter whether the image was grayscale or colored, we turned it into color. Somehow it's way easier to have a pipeline where you have only one version of the data. We could have turned everything to gray, but we assumed that color might be informative, so we turned it to color. One thing that one might want to keep a bit in mind is that the actual architecture of a convolutional network can either accommodate color or gray images. If you want to pass gray images into a neural network built for colors, you will have to repeat the luminance to R, G, and B and make it somehow an RGB color. That's what we're doing here, just to be on the safe side. The other one is that these images can be rather big, but we assume that the center is more informative. So the first thing we do is that we crop an image of 400 by 400 in the center, right? Because somehow anything near the edges we assume has less information, right? If you remember well, the task we had, we were aiming at was inferring the century at which a picture was taken just from the image. And then the next one, and that's the part that does the data augmentation, says that at the same time, scale the image randomly, either shrink it or grow it. The 400 by 400 central image that we have, we've already cropped it. So scale it up or down randomly, and crop a random box inside that image of size 150 by 150. So what this means is that it means take a random rectangle from a stretched or not version of the image inside more or less the center of the image. Afterwards, what we do is that in this pipeline, everything is, until this point, a pill image, right? A Python imaging library image. And eventually, we need to convert it into what PyTorch understands, which would be a tensor. The other thing we do at the very end, once the images have become tensors, essentially just a different data container containing the same information, is that we need to normalize, right? As we go into machine learning, images more or less assign bytes and values from 0 to 255 to pixels, but what we want to do is make numbers between 0 and 1, right? Somehow machine learning and CNNs, it's all about statistics, and operating on bytes doesn't make much sense. It's more expensive to use these floating number representations, but we need soft computation. If we look a bit at the inference pipeline, it's much simpler. Essentially, it just crops the middle 150 by 150 pixels. What we should point out here is that some networks only tolerate specific sized input images. Some others tolerate variable width and height, and some others tolerate variable only width. For example, when you're dealing with OCR or HCR, that's usually the case. You normalize the height and have variable width. And in some cases, there is usually, when you have fluctuations allowed, there is a minimum image allowed, and probably memory gives you an upper bound on how big your image can be. So preprocessing is quite important, because that's probably, if you really want to improve a bit a model that's training, that might be the best place to try, right? It might very well be that the whole code that describes a network and then trains it and everything should stay exactly the same and never be meddled with. It might have to be the data that has to be properly curated, and that could improve performance incredibly. In the PyTorch universe, and I'm not sure how well that was covered in previous sessions, we have the first thing we need to do would be to define a data set for our data, right? We have many popular data sets that are already out there, and we can just import them and use them. So if what we want to do is become familiar with actually the models or the training dynamics or whatever, we never need to write this. But the moment we want to use our own data, writing such a class is where it all begins. And to be honest, it might very well be for someone, for example, wanting to do distant seeing, that's all they got to do, right? They might find a very nice pipeline that does everything else, and all they got to do is more or less pack the data in a format that the pipeline will accept, and maybe be a bit critical about how the data is preprocessed. So somehow this happens to be probably the second most important thing someone who doesn't really want to dive deep into machine learning but wants to train their own things on their own data might have to do. A data set in PyTorch somehow is supposed to be a bit like an array. In Python we can overload operators, right? And the get item is the function we define in order to overload the operator of the bracket, more or less what Python arrays have. And the len is the method we define in order to have a len function working on an object. So essentially, this is supposed to be behaving a bit like an array. An array of what? An array of tuples, where the input tensor would be the first item, and the target, the ground truth, more or less, what the model must emit will be the second. They must be tensors, and they must have specific dimensions, because otherwise this will not really work. So we're quite free to do anything we want in here, but the output should have specific dimensions. So if we walk a bit through the lines here, right, of the get item, we have a list of paths that we got when we were constructed, and then we load the image from the hard drive, we preprocess it, and then we take the file name and we split it. We more or less hack around the file name because that's where we chose to put the class names, right? So somehow, instead of keeping two files, one with the ground truth and one with the images, we decided that the file name of the image can contain the ground truth. It was much simpler that way, much denser. That's a small hack that can be quite useful often. So here what we do is that we take the name of the class and we make a number out of it, right? We have this dictionary here, and that allows us more or less to make a number here. So normally, as we said, the output of the get item must be tensors, but if we give out an integer, it will implicitly convert it to a tensor of that integer, so that's not a problem. Integers are also allowed to be emitted. And the length should just tell us how many samples our dataset has, right? So here now, here, more or less what we do is that we define some global parameters that have to do with how we're training things, right? We have the learning rate, the batch size, the probability of dropout. We decided to have an experiment name in case we want to run many of them so that we can differentiate a bit how we're saving things, etc. And we will talk a bit about what these are later. We will come back to these parameters here, but somehow it made sense to put all the global, let's say, parameters in one place. So when the moment we have our data, the first thing we want to do is that, as we've said many times, the first thing we do is split it into train and test set. Okay, so somehow, as we saw earlier, the dataset class is more or less constructed with a list of files, and that's what it stores internally, right? So somehow, whether we have a million files or 100 files, it doesn't take more memory. the cost of that being that we have to load the image every time we want to see it, rather than if we could fit everything in memory, it might be faster when we're training. But that trade-off of memory versus speed, more or less the trade-off of caching, is something you always have to deal with. So the first thing we do is that we want to randomly separate images into train and test. And in order to do that, but also be deterministic, somehow being able, for example, to debug our code and reproduce it, what we do is that we set a specific random key. Right? If, for example, we would like to see a different partition of our data, we might change that. But it wouldn't be methodologically correct to do this kind of cross-validation on a large scale. We could do it on a toy example like we're doing here, but somehow on a large scale is not so much, because we must never draw conclusions from the test data. And so we train our paths more or less. We split our paths in three, right? We have a train set, we have a validation set to make informed decisions, as we mentioned earlier, and then we have a test set, right? What kind of decisions can we make with the validation set? When should we stop training? That's a good example, right? Maybe training all the way to 1,000 epochs is too much and the model overfits. In order to make that informed decision and yet not cheat, we need to be using the validation set. And as we can see, since we've already created this century dataset class, all we do here is just instantiate the dataset, right? And the dataset takes two things, right? A list of file names and what the preprocessor is, right? So we can see, for example, that the train set gets the preprocessor that augments, that shuffles a bit the data and makes it a bit harder, a bit different every time we read them, while the validation and test takes the one that is purely deterministic, somehow what we thought would be the best, the easiest thing for the neural network to come to conclusions. The next step now conceptually, right, we established what is a dataset. A dataset is more or less a collection of items associated with what they should be classified as. We have then the notion of the data loader. The data loader has to do with batches, right? So when we're training neural networks, we should always make a decision after seeing some data. In the very original formulation, the whole idea was that we compute our error for the whole data set and then change the model to reduce that. But somehow, if we do that, the steps, if you remember the gradient descent plots, more or less this thing about trying to walk in a mountain with fog and find the lowest path in the valley. When we're doing that, if we train on the whole data set, the steps are way too small, right, and too conservative. On the other hand, if we only looked at one image, oh, how were we wrong on this image? Let's follow whatever conclusions we come to from one image. Then we would be more or less jumping around chaotically. So what we're doing is actually selecting batches, something like 10 or 20 or 100 images, so that somehow on this trade-off of being conservative or wild when we're looking for the best solution and how to improve our model, we are somewhere in the middle, in the mid-range, right? So the batch essentially came to be as a notion because of that, and we have to pack images together. There is also a computational side to it. the way these neural networks run so effectively on GPUs is that they do things in parallel. And whenever we have a batch, every image is processed simultaneously inside it. So there is also a computational aspect saying that if we have a batch of 1 or a batch of 32, it might very well be the case, especially with small data, that they cost the same time to compute. So somehow, how many things we put in the batch can be literally how much we accelerate our code, right? The problem with the batch is that what's done here under the hood is what we call collation, right? So somehow, as we said, an image is a tensor of 3 dimensions, right? Like color, width, and height. And then inside of that, we get the value for every pixel. But the moment we have a batch, we have a new dimension. It's the 4th one, which is what batch item it is, right? So is it the first image, the second image, the third image in the batch? And the same thing applies to ground truth, right? So in ground truth, in this case, we had integers. But when we make a batch, the integers become an array, right? One integer for the first item, one for the second, one for the third, etc. So because of this collation process and the idea that the batch is using more or less many items from the dataset at once to stitch them all together, there is a bit of an issue of multiprocessing when we're making a data loader, right? It might very well be that your computational bottleneck, the reason you're going very slowly and not using all of your great GPUs you're paying for, is that the preprocessing, one by one for all the images, is so slow that the GPU, even if the GPU is instant, it's never enough. So be a bit aware of the fact that the data loader should be done in parallel, and that might have to do with why your performance is terrible or way worse than what people tell you it should be. So we made the data set, right? We made the data loaders. What we're now doing is that we want to say, we just want to be certain that somehow it kind of works, right? So what we're doing here is just, we're taking the 8th item from the data set, right? We say X and Y. X is usually what we consider to be the input of a neural network, especially if we read formulas and mathematical papers about them. And then this is a tensor, as we said, but we can make it an NumPy array. And then by this, we can take only the one channel of the image, because RGB is a bit different in PIL and in PyTorch, right? So somehow which dimension is the color changes between PyTorch and PIL. So there you might have a bit to shift dimensions around to see images. And then we just show the image and print the size, right? So the size is 3 by 150 by 150. As we said earlier in the previous sessions, right? Here's where we defined our model. If I remember correctly, this model is slightly bigger than the other in capacity. Somehow we added bigger convolutional layers and things like that. Walking very quickly through the code, when you define a model, it's also a class. It has to be a child of the class module for Torch, right? And then is imported from Torch. And more or less, we add just data members that are layers themselves, right? So, and that's more or less all we do in the constructor, nothing else. We just add the layers to our model. In a simple CNN or a simple neural network, that's what we would do. And then we have to define the forward function so we have to define a forward function which somehow will use those layers whenever information comes through. Forward is used both when we do inference, which means just using a network, or when we're training it, right? One of the great things about PyTorch is that there's also a backward function, but PyTorch will create it automatically for us. And that's more or less one of the reasons that PyTorch became so popular. It used to be that in all these frameworks, when PyTorch was coming out, in other frameworks you had to write a backward pass manually. So somehow you didn't only have to write how things are computed, but you also had to write yourself how the errors, how blame is assigned to your actual weights. This is all done under the hood automatically. And somehow, the other thing we want to see is that what we call network layers and a whole network is the same class, right? So somehow a collection of layers is also a layer. And from that point of view, if we think a bit about programming the code and how to model the code, essentially a neural network is just a layer that might have other layers inside. Now looking a bit into the forward pass, right, we can see that we differentiate between training and not, okay? So the reason for doing this differentiation, right, is for example Dropout, right? So Dropout, more or less what it does is that it erases randomly activations or neurons, I don't remember now, neurons. It erases randomly the outcome of neurons every time we run forward. It chooses some neurons and say, ignore these ones. And the result of that is that our network becomes way more robust, right? No one neuron is indispensable. That forces that thing we're doing, that we're forcing it to be redundant, makes our network somehow way harder to, more stable, let's say, in its behavior. It's also been proven that it's equivalent to training millions of networks and just taking their geometric mean on the output, right? So somehow, if we train a model with Dropout, it's a bit like training a huge committee of networks, but all in once, just with computation for one. So as we see, it's pretty simple. We define here a bit how do we want to drop out, depending on whether we're training or testing. And then we apply more or less the layers one by one on the original input data, right? So more or less we say apply a convolutional layer on the data, then apply a ReLU, and then pool, and then apply the second convolutional layer, and then apply a ReLU, because the ReLU is the same. It's an operation that doesn't have its own data to be learned, so it can be shared and reused every time, right? So we say apply a ReLU again, and then pool again. And we do that all the way until we arrive here. And this is a bit the dichotomy when we were discussing earlier how CNNs work, where we go from an image representation of the data inside the network to one where we have no longer any kind of geometry. Everything is collapsed to a single pixel practically. Every network that is a CNN and wants to talk holistically about the image has this dichotomy. How big this is versus how big these are might really have a lot to do with what you're trying to solve. If you consider that you need very abstract logic, a lot of it, but somehow the image aspects, like identifying the elements of the image, is not that hard, then you want to keep this one smaller and this one more capable. That's roughly a rule of thumb on how you could be using this, right? So just a bit, to make sure that we're safe and certain about what we're actually doing in our code, we can have a very small function as defined here that counts how many degrees of freedom, how many parameters does our neural network have, right? So we take one by one all the tensors of our neural network, and we just count how many items there are, and we print the sum. The one thing that's a bit it's good to have clear in our heads is that we've talked about tensors, right? We said PyTorch, for example, only understands tensors. But we've said earlier in the theoretical lectures that we have activations and weights. So in PyTorch, both are tensors. And PyTorch, for example, will only do operations between tensors and will only do them if they are residing on the same device. So we have to keep in mind that whenever we create such a network, it resides somewhere in memory. It could be on the GPU, it could be on the CPU. All its tensors reside somewhere in memory. If we have been careless and doing weird things, it could even be split, half of it in the CPU, half of it in the GPU. But somehow we should always be aware that a neural network lives in some device inside our computer, in some memory space inside our computer. And so do the data. And whenever data needs to go through a network, they must be in the same place. So more or less, up there we defined the class of a network, but we did not make one, right? So we actually made one instantly and erased it, this one, to count how many bytes we have. But the actual place where we actually create a network is here, right? So here's where we create the tensors, allocate the memory. We say, oh, how much dropout am I going to have? How many channels, RGB or gray level? And along with the network, we need also to define an optimizer and a loss. The loss function is the way we measure how wrong we are. The optimizer now is more or less, possibly, it's all under the hood. You never have to deal with it, with its internals. But what the optimizer is, it's the piece of software, it's an object that realizes this whole thing about the mountain descending the slope, right? So that's a bit where the error gradient resides. Essentially, every time we compute things and we go through the forward pass, if we're training, at some point on the same, more or less, time, we will get a backward pass. And at the backward pass, blame from the error will be attributed to one thing we call the gradient. This is not directly the network. The gradient is stored elsewhere, and we eventually change the network, right? So whenever we do, for example, a forward pass, the network doesn't change. We can do 100 forward passes, the network is the same. So the whole idea of who knows how the network should change in order to be able to modify it, that's what the optimizer does, right? So the optimizer knows how to change the network given how wrong everything was inside it. And the loss function, on the other hand, right? It's a function. We have many ready functions that takes the output of the network. It takes the ideal output, right, what the ground truth is, and it gives us a single number for the whole batch, right? Because the whole idea is that we want to make that number 0. That's a bit what all this optimization is about. Whenever we're talking about mathematical optimization, it's about making something very complicated become 0. That's more or less what a mathematician means when they say optimize. So the one extra thing we're going to see here that we didn't see in earlier versions of this notebook is Tensorboard X, right? So whenever we're training, we need to be monitoring our training process quite often, and in order to do that, we can be printing things on the output, but the output gets cluttered very quickly. And PyTorch, being very free, let's say, without any ego issues, thought that why write something that's perfectly done by my worst competitor? And the Tensorboard tool is the standard tool for visualizing information from networks being trained for Tensorflow, which is more or less the other universe competing with PyTorch. And they just wrote a small third-party module where people can record stuff into that system, and all the visualizations and everything is done more or less using TensorFlow technology, right? So more or less PyTorch is just using TensorFlow's visualization technology because it's really, really good and quite complicated, right? So we have at this moment defined our data loaders, which means our batches. We have defined our network, and we have defined who is our optimizer, right? The one thing we need to a bit understand, because a lot of things are happening under the hood and some of them are quite complicated conceptually. The one thing that is a very good indication of what's happening is that the optimizer we see here needs to know who he's optimizing, right? So here what we're saying is take all the tensors of the model and inform the optimizers this is what needs to become better. We could even have two models, right? We would have two networks. They would both need to go into the optimizer. That would be the case with GANs, for example. Okay. And now, when we're training an epoch, right, this is a function. It takes more or less a whole data set. It walks through it once, and it goes forward, finds the errors for every batch, goes backward, right? So in order to train an epoch of the neural network, maybe some terminology I haven't yet said is this. When we're talking about an epoch, it's the step of iterating over the whole data set. We have that versus an iteration, which means more or less going once through the network with one sample or a batch of samples. Right? So iterations is one step of walking stuff through the network. An epoch is doing it once for all the data set. How many iterations make up an epoch depends on the size of your batch size and your data set. So we have the data loader, which will be giving us batches which are randomly selected images, right? It has to be the data loader from the train set. We have the model, right? When we say model, we mean the neural network. So we have the model, which is more or less what's going to be running on our inputs. We have the optimizer, which is a bit who is aware and is maintaining all the things that need to be updated eventually when we want to. We have the loss function, which is just a function telling us how good is a prediction, but quantified in a single number. We have the device because somehow this could be an optional parameter. We could have made sure everything is at the right place. But since we're actually putting data here now, we're loading them from the data loader every time, it's a bit safer to do everything here and make sure that things are in the right device here. And then we have the epoch number, right, more or less. Is this the 7th epoch or the 20th, which we just use to log things, right? The epoch number is not really needed. Somehow the assumption that there's a sequence of epochs doesn't really affect how this works. So the first thing we do is that, as we said earlier, we migrate the neural network into the memory. If we're lucky and we have a GPU, that's where it would go. We set it to a train mode, right? Remember that there's some things happen differently when we're doing inference, some things happen differently when we're doing training. And we define some lists that will accumulate data, more or less, so that we can print a few statistics and nice things about our model. And here what we do is that we iterate over our data loader, right? This collation thing means that we had tuples of images and numbers, and the data loader makes that a tuple of many images and many numbers, right? So we have all our batch both for the images and the inputs in one thing. And once we have them in our memory, the first thing we do is that we put them to the device, whatever it might be. It might be our memory, it might be the GPU. And then the moment we walk into that loop, what we're actually iterating over is iterations, right? So somehow every pass of this loop is a single iteration of the network, right? So somehow this is kind of, let's call it PyTorch nomenclature. It doesn't really mean something. It just means put the data where it should. This means I'm beginning a new iteration. I want the optimizer to forget all they know, right? Somehow empty everything you remember. And then we say, however the model might be trained until now, we don't know, it might be totally random, but we would like to have the output of that model. One detail here we have not discussed a lot is that when we're talking about classification, the ground truth is an integer, but the way that a neural network expresses itself, it's a probability distribution. It's more or less a softmax function which assigns to every possible integer out of the ones representing our classes a distinct probability. So the ground truth might be integers. The actual output of the neural network is a whole bunch of numbers for every item. The way to interpret then that output is very simply that we take the position of the strongest value, and that is the class that the network predicts. So there is a bit of a thing that's a bit cryptic. As we said, PyTorch does a lot of things under the hood that are quite complicated. So if we see we have the optimizer, it's connected to the data, it's connected to the weights, and under the hood all of these things are communicating and computing things on each other without us ever explicitly describing that computation. But a computation graph under the hood is being constructed, and it's quite complicated and big. And so the problem might be that what is a memory leak in typical programming can become a very big problem and way harder to understand and train. in PyTorch, right? So whenever we're doing this automatic error gradient stuff, automatic differentiation is the name of the technology. If someone somehow influences someone else, unless both of them are dead, there's always a link, a pointer, keeping both alive, right? So we might delete something and it might still stay in memory, and that's what memory leaks are. And whenever we see a detach, it's about handling that. Practically, for an early practitioner in PyTorch, what it means is that when you see a detach, don't ignore it. It looks weird. It might seem it's useless, but it might, for example, 10 minutes later, blow a bug. If you're not using correctly the detach wherever you saw it, because you always start with a skeleton of an example, if you don't use the detach correctly and you don't manipulate your computation graph that's constructed under the hood correctly, you might have big problems, right? So use this a bit as a sign of alarm. If it's there, respect it. And maybe there are cases where if you somehow are running out of memory when you shouldn't, a detach might be missing in something you did. The easiest example here would be this. Without a detach, if I want to keep the average of the outputs for all iterations, just so that I can print them at the end, if I keep them in tensors and I don't detach, that means that none of the data can be freed from memory. So suddenly we can end up having the whole data set in memory. We might even end up having the whole forward passes of all the data set in memory. It might be quite catastrophic. So yeah, consider that a bit cryptic, a bit black. Usually you don't have to deal with it. And if you follow the simple tutorials you find online, it never becomes a problem. So this detach we could maybe ignore. The three fundamental steps would be that first we tell the optimizer, forget everything you know, start from scratch. Then we say compute the output of the network, whatever you know. Then we say compare the output to whatever should have been there and tell me how bad it was. Then we say that number you computed, that is the number that should have become 0. And somehow, this is a bit what informs the optimizer of whatever it has to do, right? So the optimizer will do whatever it has to do just because here we said loss backward. And then what we say is that, okay, the optimizer formed an opinion on how things should change, right? Actually, the heavy computation is essentially happening between those two lines, right? So from the moment we call backward until before we call this line runs, that's a bit where the heavy computation of training happens. And then we say step, and that just means whatever the optimizer thought the network should become, apply it with a bit of caution, right? That's what the learning rate is. So the optimizer has an opinion on how should the network be in order to have the minimal error. But if we move the network all the way there, we become very, very volatile, very daring. So the learning rate says, you know what, just do 5% of what you thought, and that's enough to improve the model. Or 1 per 1,000, to be more exact. That's a kind of standard setting for this kind of network. So what we're doing afterwards is that we're just accumulating our losses, our predictions, our targets, so that we can have some numbers to see a bit the dynamics of training. And then outside of the loop, all the data we recorded on how every iteration performed, we're concatenating them into big things. We make a bit of performance evaluation, but on the test set, on the train set, sorry. So somehow this is not supposed to be highly informative, but somehow it tells us as the network is maturing how well it performs on the data it is aware of. And here, this command, more or less, what it's doing is that it's starting Tensorboard. Okay, so Tensorboard is a whole website where you see all your data in a very rich manner. Putting it inside a notebook, it's like putting a website inside a website. It's a bit complicated, a bit annoying. That's why we have all these steps. If you were working on your own machine, what you would be doing is that you would be launching Tensorboard independently, and you would have two windows, one where you're looking the training, one where the actual training is happening. So a bit on understanding how Tensorboard works internally, it's built on top of this Google protobuf library, which more or less is how Google stores their stuff, whatever they're doing. And every time you run a new training, a new directory is made with some dates and some other parameters. So a new directory is created, and inside that directory, whenever you're recording informations, you're actually data is being stored. And then this website here, right, which is a whole web server, essentially, is reading that directory and trying to show you whatever was recorded in there. So these two things are totally asynchronous, right? One program is running training and storing whatever it can in this cryptic format called Tensorboard, and the other program is taking whatever data is there and tries to make you see it. If you're really storing a lot of stuff here, these directories can become very big. You might have to start erasing things after you run them and stuff like that. So now we have this whole, let's say, website running inside our machine. As I said, the Colab now is running on the same, has given me the same virtual machine I had earlier where I rehearsed this. So we already have some executions. But in your case, this wouldn't show, if you run this for the first time on a new machine, at this point in the notebook, this will not appear, right? Don't worry, it's not that there's a bug. It's meant to appear the moment you start to actually train stuff. Here we have a function that is about evaluating an epoch, right? It says, how do I evaluate an epoch? How do I see how well it did? And more or less, it does whatever we did before, but without the backward stuff, right? So if we look a bit into it, we take a lot less parameters, because if we don't have the backward stuff, less things are involved. We just have the data, the model, and what we do is that we do the same stuff we did before, right? But here we say with torch no grad. That somehow means that whatever happens under this context should not be keeping all these complicated links of anything that touched anything else. It's a bit as if we were doing it, it touched on every single variable and tensor in here, right? So somehow, if you're sure that you're using PyTorch, but you're not using it for training, it's way faster and way simpler to always work in such a context, right? Somehow you're saying to PyTorch, no, I just want you for simple computation. Act a bit as if you were NumPy or a simple algebra library. So we iterate once more through the dataset. In this case, this might be the validation or the test dataset. And we go and we record a bit the performance metrics that we would like to show. and we're returning just some variables that we consider they are informative. And we run this evaluation code in the very end of this block, and as we can see, the model is untrained, and that's why it has a 51% accuracy, more or less flipping a coin, right? Because the problem has two classes, like 19th or 20th century, and this has a 51% accuracy. That's exactly what we would expect. The moment we're actually training data is this loop here, right? So more or less, the functions we defined earlier is about how to do one epoch, but we don't know if we had 100 or 1,000 or whatever. This is a bit the code where we say, you know what, I want to do 10 epochs. This is a bit our whole training. And this is also where we record our stuff for Tensorboard, right? So whatever was already there in Tensorboard existed from previous runs. Actually, this is the first time we write in Tensorboard. If we look at this code, how we structure it is quite useful, right? The same design paradigm can be used also for training, for having training scripts. And the idea is that somehow we never explicitly say what epochs should be. We just say that make sure it's not above 10. And if it's not above 10, you will increment it by 1 this way. If we design our code this way, more or less, we can resume for free, right? So practically, all we need in order to resume for free is to make sure that we will not initialize randomly our model, right? We could, for example, be loading from the hard drive. We'll see that in the next block. And that we do not set the epoch count to 0. And that way, if we say whatever your state might be, just make it sure that you arrive to epoch 10, we can have resumable code. And so here goes the actual training, right? And if we see this scroll bar, right, that's just a nice utility from TQDM that more or less makes any loop give you a scroll bar. But what we're actually looking here is iterations over the whole data set, right? So the whole data set is split into 25. The whole train set is split into 25 batches, and we can see that roughly we need 2 seconds per batch, right? That's on a relatively strong single core CPU kind of running. The GPU would be extremely faster, right? At this moment, we're running everything in small virtual machines online. That's more or less what anyone can get just with a Gmail account. But this is not the speed we would normally get. Okay, if we had a GPU and we're running this code on our machine. So we've only done one epoch here, right? We can see the tests, the train set, and we can see the validation set, which is way smaller. It's 10 epochs. There is a bug here. And if this trains, and this will take some time, just for 10 epochs, this will take some time, we will see how we could, for example, we're actually saving the model at every epoch, right? And we can see how we could resume training just by creating a new model, loading whatever was on the hard drive for its weights, and and that's how we can more or less resume whatever we have, right? So somehow resuming a training that got interrupted, that would mean more or less running these two lines, creating a new model, and then just rerunning this as many times as we need until we're done. It might be quite convenient to somehow make a function that will create a new model if nothing is on the hard drive, and use whatever is on the hard drive if available. If you put those into one function, suddenly all you say is that I want a model to train. I don't care how exactly it's constructed. And it simplifies your training pipeline quite a lot. Right? The one thing we should look a bit into is this line here, right? So we created a model. Memory was allocated with random weights. It's done as we did it the first time, right? This line more or less means make just a new model. Here, what we're saying is that take your state dictionary, right? So somehow all the layers you have, what are their tensor values, from whatever you loaded from this file here. It is customary, although code doesn't break in any way, to have tensor weights, tensor values saved on the hard drive as a PT file. It's kind of standard, but you can just ignore it if you have reason. As this is still computing, let's talk a bit about the hackathon and talk a bit about so more or less every team was given these notebooks. They were walked through them, and they were also given a skeleton that is the analogous of whatever is in these Colab notebooks, but as a simple code. And in the end, their instructions were: you have 3 hours, experiment on Colab, try to change some things in order to become better. I'm not telling you how. The hint they were given is that preprocessing might be the best place to search, and maybe a bit making the network bigger or smaller. And then, given that they were restricted in hardware, as we see, training in Colab 10 epochs takes several minutes, so you cannot really try it aggressively. We told them that we're going to compute for 200 epochs afterwards. So we're going to compute the heavy stuff, right? And the teams were supposed to more or less tweak the thing so that if ever computed heavily, it would be the best thing, the best solution. The code that we received was of very high quality. There were a few things in the scripts that we had to change so that the code would work exactly the same in our test case. Actually, yes. What we did is that, right? We were given notebooks and we made scripts out of them. But then we needed to tweak a few things for some teams. If I remember well, there was 1 or 2 teams where it worked out of the box. What we see in this README file is exactly how we tested the code, right? That's not so much what we care about. What we mostly care about is how these different executions trained, right? So we had 5 people trying slightly different ideas on 5 teams, 5 entities, trying slightly different ideas on what we can get. And we measured their training error, their validation error, and their test error. Okay, so if we look at it, Team 2 actually outperformed the baseline, which is quite impressive, right? People with practically zero or very, very limited experience, within 2 hours, managed to take something that was more or less improvised by, let's say, experienced practitioners within a day or two, and they managed to take that and improve on it. It's actually, in my opinion, spectacular, like beyond any expectation. I expected that they might have had a better, validation error or train error. Maybe they could overfit something, but no, they had actually an improvement on data that were never seen, never touched by them or anyone else. Now, there's a bit of a question: is 0.5% or 0.7% significant? The data set is not that big, right? We have a binary classification. The test set, if I remember correctly, is 500. So that means something like that they got 3 or 4 samples more right than the baseline. But still, although it might not be very strong statistically as a demonstrable, let's say, as a proof that this is better in all cases, this would be better in another unseen second test set. It's a very strong indication. And we can see here a bit from Tensorboard, more or less, the curves, right, of how the models were behaving. One thing that is quite important, you must never forget when you're training, is that these lines you see with bright colors are the smooth lines. If you look at the actual performance, they're the opaque lines that are really volatile, right? So one iteration, and that's a bit to understand about this trade-off between being conservative and being daring. We might have things that more or less are wrong, but very, very slowly they move us towards the right direction, right? So somehow, if we think about it, what we're doing is that we're actually jumping randomly, but slightly more forward than backward. And that's how a neural network is trained normally. If these curves were, let's say, smooth like that, without the actual iteration question, it might be an indication that we are too conservative, right? So somehow the training has to be volatile. We have to go even depending on the data set. We might need several epochs to form an opinion on are we progressing or not. And that has also to do with how you would set your stopping criteria, right? When would you choose to stop training? It has a lot to do with that. It should maybe stop training if I haven't improved for 10 epochs, right? Maybe 1 epoch not improving is quite to be expected. Another thing that might be interesting is that we could use a nice tool in order to see what they did differently, right? So we see that team 2 is the one that outperformed the baseline. Everyone else, they did quite well. They did not reduce performance, right? While they were not seeing what would happen, because they trained for a lot shorter times than they were tested on. So no one did bad. But let me maybe this. Sorry. This should be, I guess, bigger. Right. This is visible, right? Okay, so There is this very nice graphical tool from programming that does more or less a visual diff between files. And we could maybe see a bit the difference between let's say the baseline interpreted as a script and team 2, which is the winner. Right. So as you can see, I'm not sure if this is well visible on the screen. What Meld does is that it takes two pieces of code and it shows you the difference. It's actually designed for something quite more complicated, which is to choose how they should become one. Right? So whenever you use it with caution, because you might, if you change things, you might end up changing the files. But you can also use it just to see differences. Right? So more or less, team 2 is on the right, and the baseline is on the left. Right? So yeah, this Google Colab thing is not needed when you're running, let's say, as a script rather than as a Colab notebook. So that's totally fine to be missing. And actually, this is the first piece of code that's missing. It seems to be redundant, right? Because somehow it's already resized to 150 by 150 and they just resized to that same thing. That's probably why they commented out, right? So somehow they changed the resizing. If I'm not mistaken, what they did is that they made it, they made the scale more or less be always 1, right? While here is between 0.08 and 1, they made it be always 1. That's one difference we can see. We can also see for the validation processor that it's that is somehow using randomness as well. That's quite surprising why this might improve. It might be that cropping 150 pixels in the middle is way too little, and somehow maybe randomly getting around you might end up getting more information. But it's an interesting finding that could be further investigated. And as we see, they added that measurement to appear directly on Tensorboard, while before it was only appearing on the command line. So the take-home message from this is that if you're a practitioner that wants to dive a bit into those things, what you're going to be essentially dealing with will be two things. You will have a pipeline and let's say software that might be millions of lines of code overall. Like everything you're using can be millions of lines of code. You will probably have to identify the 300 lines of code that matter, right? Or the 100 lines of code that matter. the very high level stuff, the stuff where actually you make critical decisions. And then out of those 100 lines, you will have to have a good understanding of them, a proper understanding of them, and maybe change 2 or 3 lines. And that might be work of weeks and months, right? So somehow, how deep learning is compared to, let's say, coding, the skills you need might be the same or very similar. How you do it, it's extremely different, right? It has a lot to do with reading and understanding what's happening, and a very little to do with actually writing complicated things. Almost always, there is going to be something very similar to what you need online, right? More or less, what you have to do is what people would call gluing code, right? So you might want to pack your data into an existing pipeline. That's probably the standard use case for you. Or maybe, I'm not sure, run a cascade of 2 networks, somehow the output of one becoming input for the other manually, right? That's the kind of thing that you might need. So somehow reading this code is intimidating, but you should not avoid it. And considering it totally foreign, if things work for you, great. But the moment you need to change one thing, it's going to probably go very bad for you if you don't have an understanding of what's happening. So somehow, the moment you feel you need to change anything, you should know the fundamentals of how PyTorch works in general, or TensorFlow for that matter, right? TensorFlow and PyTorch are quite equivalent, and usually you will find the models you need. You will find in both, right? It's very rare. It has to be very cryptic what you're doing to only find in one of the 2 paradigms.